Hi and welcome to this course, ETABS Building Structural Design according to ACI or ASCE 318-19. This is the introduction. Introduction to ETABS. It is the first chapter. So we discuss design criteria, ETABS user interface, and create a new model. Also, we need to get know floors and grid system and how to modify it in order to also to input the design data and units. And Model Explorer is a good explorer in ETABS. Also, the other chapter will be preliminary design. We will read the architectural drawings, design loads, and combinations, in addition to making a preliminary dimensions for the slab, ribs the slab, beams, and columns. In the next chapter, which is ETABS Modeling, we will define the material and column section properties, beams, and slab section properties, in addition to wall sections. Then defining a group, defining the load patterns and load combinations. Drawing grids, modeling the first floor of beams, columns, walls, and opening. Assign restraints to base supports, footing. Load assigns, group assigns. Replicate the floor for other floors. 3D view and extruding, and symbology for the objects. Drawing a column strips and middle strips, or design strips. In the next chapter, structural analysis, we will make a mesh, a general mesh for walls and floors. And then we need to make a check from the model. Then we will run the analysis and do 3 checks: compatibility check, equilibrium check, internal forces check, such as section cut or the internal forces in columns. Serviceability check, deflection, according to ACI code. The next chapter will be structural design ETABS, initializing column design for ETABS, import the design load and load pattern factor, concrete frame design overrides, and selecting the load combinations for design and envelope one, selecting design groups, slab design preferences, recover and bar sizes preferred, slab design load combinations and storage, running the design, all members pass check, and verify analysis vs design section check, display frame design information, display slab design strips design method, display slab design finite design method. The next one will be design of beams for flexural, torsion, and shear. Also for the columns, we will explain the axial load and the interaction diagrams, in addition to the design according to ETABS. Design of the slab for flexural and for shear according to design strips and finite method, shrinkage steel, and how to make and generate ETABS report, and how to export this report and design data to Excel. Finally, we will talk about job drawing and the free AutoCAD drawing has been. Again, for now we are going to talk about the design criteria for this project. Reinforced concrete 3 floors office. So this is our building that we are gonna build and design in ETABS. The floor height each 4.1 meter. So we have 3 floors of 4.1 floor height. A concrete FC prime, which is the cylindrical test for a concrete with 28 days of curing, and steel grade 60. So this is the grade 60, which is KSI. So it is evaluated to if yielding 420 megapascal. The reinforced concrete that we have 2 shear walls of thickness 0.35 or 350 millimeters. Also, the slab system that we are going to design is a 2-way using a one system. This is the criteria that we're going to use a one system, such as solid, non-solid, like waffle, ribbed, voided, or flat plates, flat slab, and so on. But because the thickness that we evaluated, or it will be 0.4 meter, which is 400 millimeter, and this is so high to be solid. So our case is to be economical. So we are gonna use the waffle slab or rib slab, but waffle slab it is more effective than rib slab, because in rib slab you would like to load the block weights itself. Unlike the waffle slab, the mold will be very light. So this is what we are gonna do. Exploring ETABS interface. Here we have a file. From file option, you can create a new model or open an existing model. Save for saving this model. Save a copy from this model. Import, like import ETABS E2K text file. This text file allows you to open this model in a previous or older versions of ETABS. From export, you can export also A2K or export the model as DXF for AutoCAD file. From edit, you can edit a lot of things like frames, shells, grids, replicate, extrude points, and other options. From a view, you can view a 3D view, plan view, zoom in, zoom out. From define, you can define material properties of steel and FC prime concrete, section properties for frame sections, beams, and columns, slab sections or wall sections. Also, you can define load patterns, such as dead load, live load, super dead, wind load, snow load, and other load patterns. Also, you can define load combinations. From draw, you can draw a lot of things, such as grids. Select, you can select structural element based on object type, like walls, beams, columns, floors. Also, you can deselect them. From assign, you can assign joint, restraints to be fixed, or frame section property to change it, or shell loads, frame loads, join loads. From analyze, you can check the model before analysis, set the mesh size to be, for example, 0.25 meter. From analyze, you can run the analysis or by pressing F5. From display, you can display a lot of things like load assigns on frame and force stresses. Design, from this option, you can design the model by clicking on concrete frame design. If it is a project of steel, you can press this option. From options, there is a lot of options like graphic colors, graphic preferences of font size, and others. Here we have in the workspace 3 spaces. First one is Model Explorer. This will allows you to explore the model, like groups, loads, properties, structural layout, and other options. At the left, we have a lot of elements or tools that can allow you to draw beams, columns, slabs, openings, and a lot of things. In the middle, we have a plan view. We can change it by pressing on 3D or elevation. Now we have 2 3D. I will change this to plan. I will select the story and click on close. So I have XY plan and 3D view of XYZ. This is for our lesson today. See you later. Hi again. To create a new model, go to File menu. Click New Model or Ctrl-N. We have here 3 options. For the first option, you can use a saved user default setting. Second option, you can use a model template from previous model. Or in this case, we will use built-in setting for metric SI unit, and the material will be in United States. Here for the steel design code, and our code will be for concrete, reinforced concrete, so use ACI 318.19. Click OK. Now we are going to talk about XYZ for grid system in ETABS. X in this direction, Y out of the plane in the paper, out of your view, Z representing the floor heights, and XY plan or plane, this is XY plane, this is XY plane, and the 3D view will show you X, Y, Z coordinate for the 3D view of the structure building. Now going to ETABS, after creating a model, we can import the number of grids in the X direction. The number of grids in X direction are the lines that crossing the X direction, the X axis. For example, if this is a one floor, I will have this line and this line that crossing the starting and ending and joints of the X axis. So 1, 2, we have 2 grids here, but let's take it 4, and the number of Y direction is the lines or the grid lines that crossing the Y direction. For now, it is also 2. This is 1 and this is 2. Let it to be 5 spacing of grids in the X direction. You can input a uniform spacing, but you can edit it later. Assume it is 6, and here 8. The spacing of grids in Y direction. This is the Y, and the spacing of grids in the Y direction. Assume we have 5 grids, so the spacing between them are 8 meters. Now you can specify for the Z direction here the stories. The number of stories, assume it is 8. Typical height, assume it is 4 meter. And bottom story height, also assume it is 4 meter. Ensure that you are clicking on grid only and press OK. Here we can have the XZ plane, X, Y plane, and here we have the 3D view of X, Y, Z. Z representing the number of floors, Y in this direction, X in this direction. And this is the XY plane. So after we making the grids, we can modify it by right click, add modify grids, modify show grid system, rename the system grid name if you want. For example, grid system 1. We have ordinate and spacing. If you want to display as ordinate, you can see the ordinate of X grid data ABCD, alphabetic ABCD, and Y grid data 1 up to 5. For X ordinate for the X grid data, you can see it and you can change it if you want. But the simplest way is to go to spacing, display grid data as spacing. So you can see for A, the X spacing is 5 meter, which means 5 meter from A and B. You can change it, for example 4, and this 6, and between C and D 8. For Y grid data also you can change it. Let's assume 8, 9, 6, 5. You can change the color of the grids as you want, the bubble size. After making all of these changes, click OK. Click Review, refresh view, and see what will happen now for the grid. It's changed. Make sure to save your project. Go to File menu, click Save As, and save the project. Name it in the path you would like. Then save. I saved it. So next step, we will talk about units. If you go to the bottom corner, left corner, you will see units. Click on it and make sure to select metric SI defaults for our project. The second thing is to go to consistent units. Make sure to set up the length unit to be in millimeter, in meter. First unit to be in kilonewton, and temperature to be in Celsius. After that, go to show units form and have a look for the table. You can change the decimal places so you will have more accuracy. The next thing that I would like to share, design code. Go to design menu, concrete frame design. So our project is reinforced concrete, not steel. And go to view revise preferences. The first option is design code. Make sure to select ACI 318/19. There is a lot of codes like urban codes and other codes. In our case, it is ACI 318/19. Other things we will talk about it later, and this is for now. For now, we are going to talk about Modal Explorer. Modal Explorer, you can, if you don't see it, you can go to view menu, go to options menu, and go at the last one, show model explorer. You can see it. You can expand it as you want. So we have model, display, tables, reports. Model, you can see, you can expand it by clicking the plus button. We have a project, like project information. If you click in it, you can change it. As you can go to file menu and you can click here. The same thing. We have structural layout like stories, number of stories. We have 8 stories. So you can explore, it's like you can explore what is going, what structural elements you have, properties like frame sections, walls, etc. From display, you can display, for example, 3D view. You can display a lot of things like view. For example, for 3D view, I want to change it to plan. So it's a plan, or I want to change it's like an elevation. The same thing as you can change it from here. Elevation, and you can set the elevation for B, for example. You can see the elevation B. Also, you can have tables. After you make design, you can show the design data, references, and so on. And you can have reports, like summary report or project report. This is for the Model Explorer. For now, we are going to talk about the architectural layout. As you can see, this is our building layout. We are gonna design using ETABS. So here we go, 2.5 cantilever and 8, 8, 8, 8, 4 spans of 8 meter. And here 2 spans of 8 meter and 3 spans of 9.5 meter. Wow, it's so long. So Waffle, it will be the best solution for this. You can see we have 2 shear walls, and in addition to an opening with 3 by 6 meter. So these are our columns. They are 20. You count them, 20 columns. And we have a circular beam. We're gonna draw it using ETABS or AutoCAD. And this is, so see you later. Design loads. We have a superimposed dead load, 3 kN per meter square. This is superimposed coming from plastering and tiles and other things, finishes. So it's approximated to be 3 kN per meter square. Live load of 5 kN per meter square as adapted from live loads extracted from ACI 7/2020 table 4.31. Illustrated that for office buildings, you should take 5 kN per meter square for lobbies and first floor corridors. For offices, you can take it lowest, 2.5, and for corridors above the first floor, you can take it 4 kN per meter square. But in our case, we will take the largest one to make it more simple for the calculations and design. Also, we have a perimeter wall, a weight of 6 kN per meter. This is a perimeter wall for an external wall. It will be applied in this, at the perimeter of our layout or building layout. So in these spans or in these beams, external beams will be applied only for its weight and for a perimeter wall of 6 kN per meter, also some portion of the slab, according to tributary area, as we will explain later. Load combinations. According to ACI code, there is a lot of load combinations. First one is 1.4 dead load. Dead load consisting of the own weight of slab and the structural elements like columns, beams, all of this are own weight. In addition to super dead load. So super dead load is added to the dead load. The second one, 1.2 dead plus 1.6 live plus 0.5 live roof or S or R. So in our case, we will use 1.2 dead plus 1.6 live, and we will ignore the other thing because we don't have roof or snow. So yeah, that's it. R is for seismic load, and our project will be in gravity, designed for gravity only. So we will use these two and other things like there is also snow or wind load, E for seismic also. So we don't need all of this. We will design based on these two load combinations, and we will design for the envelope one. Thickness of the slab. In one-way solid, the minimum thickness is for the critical panel. So it is for one end continuous span. Thus, the minimum slab depth will be L over 24, which gives us 9.5, the highest dimension for the critical panel, over 24, which equal 0.39 meter. But our slab system is a two-way, therefore the preliminary slab thickness would be decreased. Note that this table is for deflection consideration only. So maybe the loads, if they are high, may affect this thickness. So we use a starting point for H equal 400 millimeter for the whole slab thickness. After we choose the thickness for the slab, which is 0.4 meter, know that 0.4 meter is too high to being a solid slab, so the thickness will be large and therefore the weight will be large. So the moments and design will be special for this case. So we need to use a better solution like ribbed slab or waffle slab. We chose the waffle slab because it is more lightweight. So unlike the ribs or ribbed slab, because you need to loading the block weights. So in this case, we need to use a waffle slab. Therefore, we need to find out what is the mold. You need to find out or discovering a mold in the internet. So you need to find out which is best for you for this case. We found a mold with this characteristic. This is a section of the slab that would be, this is the mold. And you can see the spacing between each two ribs is 0.8 meter. And the bottom ribs or rib width is 0.125. The top will be 0.255 and the average will be 0.19 meter. Therefore, we need to find out the slab load. It is 1.2 by the 3, which is super dead, plus 5.55 is the slab unit weight. The slab unit weight. If we used this mold, note that the mold is 0.3 height and we have a topping of 0.1 meter. So the whole depth will be 0.4. So 1.2, 3 plus 5.55 plus 1.6 multiplied by the live load, which is 5 kilonewton per meter. Square this gives us 18.26. This load we will use later for designing the slab and also to find out the preliminary dimensions for the columns. For now, we are going to talk about beam preliminary dimensions. So the beam width would be more than 200 millimeter and B also would be 0.3 to 0.5 the total thickness H. Therefore, assume P, you can assume PL over 20. L we have 9.5, which is the maximum in the panels, so 9.5 over 20. This gives us 0.5 meter. But to avoid the problems related to deflections and slab thickness and so forth, we need to increase this to increase the depth for the beams, for the main beams, to make them stiff enough. So you know, the alpha m, which is in the ACI coefficient, in the ACI code, which is related to the moment of inertia of beam over moment of inertia of slab. We need to increase this ratio, which means to make the beams stiff enough. So the slab will be adequate for deflection. So we need to find out. We can take 9.5 over 18.5. This gives us some value, but you need to increase it a little bit. So I increased it by half, 1.5. So we can increase it by 30% to 50%. This gives us about 0.77, and we will use 0.9 meter for the beams. So I increase it more than 50%. Again, this is because the deflections, and we will see it later in the ETABS. We win. While we are going to add the combination for deflection, long-term deflection, we will see that 0.9 is okay. So this is for the main beams. Also, we have another two beams groups, which is for the circular cantilever, that we will choose a 0.4 by 0.6 meter dimensions for the beam because it has a lot of torsions. So we need also to add an inclined beam, as we will explain in the AutoCAD. So going to AutoCAD, here we have. So we need to add main beams in the X direction and Y direction of 0.9 by 0.5, 0.9 by 0.5, and here we're gonna do some inclined beams also by 0.5 by 0.5, 0.9 by 0.5 meter, and this is the circular beam will carry some portion of the slab because we add an inclined beam. See, so we need only to make it 0.4 by 0.6 meter. Rather than this beam or this cantilever, we need to extend these beams in the X direction, so they will touch this corner or this edge. So they will be cantilever in this end, and therefore we need to add or to make this beam only 0.4 by 0.4 meter. For now, we are going to talk about preliminary dimensions of columns. There is a general rule that says that columns carry its cross-sectional area. There is a more accurate rule. The ultimate on the column is equal to the area, the cross-sectional area of the column in centimeter square, by the FC prime over 21. To find the preliminary dimensions of columns, we need to find the critical P ultimate. So as we said in the previous lessons, we need to find the critical column and to generalize this column dimensions for other columns. So find the critical P ultimate in this column by finding the maximum tributary area by the ultimate load in the slab, which we have found out and calculated in the previous lessons, which is 18.26 kilonewton over meter square. The second thing is to multiply this value by the number of floors. So the bottom column will carry all the floors above it. The critical column will be the interior column, as we will see in the AutoCAD, which is C4, that will carry a tributary area of 76 meters squared. Therefore, P ultimate is equal to 76 by 3 by 18.6, which equal to 4,164 kilonewton. If you take a quick look for the layout, you can see that, for example, this column will carry this area, the tributary area that you need to take this point, the area will be this area. You need to take the midpoints of the nearest spans. This span, the mid area, or the midpoint is here, and this shear wall, the midpoint is here, and this is here, and this is here also. So here is the area that the column will carry, which is the half of 8, 4, and the half of 8 is 4. So here we have 8 in X, and here we have also 8. If you take this, 8 by 8 gives us 64 meters square. And you see this, for this column there is an opening, so it will be this. As you can see, this is the same dimensions. But if you going a little above that, you can see here there 9.5 meters, and for the X are 8, 8, and this is cantilever 2.5. So as you can see, for this column, for example, 2.5 plus 4 gives us 6.5 by half of 9.5 and half of 9.5, which is 9.5. 6.5 by 9.5 gives us 61.75. So this is less than 64. If you take this column, you will see the area R, as I found out in this area command, and after that you need to select the borders of the needed area. When you finish, press T for total, and here's the total, 76 meters squared. So our tributary area is 76 meters squared. For now, we are going to talk about how to define materials. Go to Define menu, select Material Properties, add a new material, rebar for material type, United States for the region, and this is the code. Ensure it is grade 60. Click OK. Rename it for rebar G for grade 60. Go to Design Property Data, Modify. Change the minimum yield strength Fy to be 428.20 megapascal, 420 megapascal, and click OK. OK. Now we are going to define the concrete. Choose the 4000 psi, add a copy from this material, or you can add a new material. Add a copy, rename for C28, C for concrete, 28 for FC prime. Change the weight per unit volume, 25 kilonewton per meter cube. For E modulus of elasticity according to ACI code, it is according to this formula, 4700 by FC prime to power 0.5, and click enter. You can remove the digits or leave it as shown, and then go to modify show material property design data. You can delete this, but it will not affect the results. So here the value, you change it to 28. OK, and OK. For now, we are going to talk about how to define the frame sections. To define a frame sections, go to Define menu, and section properties, click frame sections. You will see already some sections have been provided. You can add a new property or copy these properties and or modify show these properties. We need to add a new property. Section shape, select concrete rectangle and select the rectangle one and name it for C column. Our column are 50 by 70 centimeters. And for material, select the C28, which have been defined. For the dimensions, we have 700 millimeters and 500 millimeters. So you need to also to add or edit the property modifiers for the column stiffener. So modify show modifiers. According to ACI, you need to modify the moment of inertia about 2 axis and 0.7 for the 3 axis. So you need to change these values. After that, click OK. You can see here the properties like moment of inertia and other things. So for now, click OK. This menu will talk about it later in the next chapter. So we need to, for now, make sure it is a design for column, not a beam, and choose the rebar that we have defined, and other things we will talk about it later. For the beams, we need to add a new material or a new property, concrete rectangle, and choose C28. We have 3 groups of beams. The first one is a B of 90 centimeters by 15 centimeters. So we need to change the width to 500 millimeters. For modifiers, for the beam, it is 0.35 and 0.35. Also this 0.35. And ensure it is a beam here. And rebar also grade 60. For the cover, leave it 60 millimeters. And click OK. Add a copy from this section. Add a copy. And change it to B. We have another beam of 60 by 40 millimeters or centimeters, and here is 60, and here is 400 millimeters. Also, we have defined already, so modifiers also have been copied. So click OK. The third section for beams, so add a new copy, is B 40 by 40 centimeters, and change the hole depth and click OK. In this lesson, we are going to talk about how to define slab section. To define a slab section, go to Define menu, Section Properties, Slab Sections. Add a new property. Name it Waffle Slab of 40 centimeters depth. For the material, C28 and shell thin or shell thick. As you want, it will not affect the design, and the effect of this will be in the footing, will be clear. For now, select the type to be waffle. Overall depth are 400 millimeters, and in the bottom 125. Spacing between ribs are 800 millimeters in the both directions. Finally, go to modifiers and change the stiffeners for this slab to be 0.25. After doing all of this, click OK, OK, OK. Now we want to define the wall section. Define section properties, wall sections. Add a new property. Name it wall 350 for the thickness. Select wall material C28. Go to modifiers, and according to ACI code, you need to change the modifiers to be 0.7 as walls. Click OK. Change the thickness. OK. Hello again. In this lesson, we are going to talk about how to define groups. If we look at this AutoCAD, we can see here is the first beam, labeled B1, which is 50 by 90 centimeters. So this is B1, and this is B2. We have a lot of beams up to B15, which is the cantilever circular beam. So we need to define 15 groups of beams. So this will make it easy for the design later. And also we have 20 columns of dimensions 50 by 70 centimeters, in addition to 2 shear walls here of thickness 0.35 meter. So for now, going to ETABS, go to Define menu and select Group Definitions. So add beam 1, add beam 2, and repeat this process until you reach B15. And for now, add the column for C1. And we need a C2 column. So add 2 definitions of groups for columns C1 and C2. After that, we need to do also a group name for the shear walls. So add W for walls, or you can name it W1 and W2 also. Finally, click OK. Hi, in this lesson, we are going to define the load patterns and load combinations. Define load patterns, go to Define menu and select Load Patterns. You can see we have dead load and live load. For the dead load, we have self-weight multiplier of 1, which means that the ETABS will automatically compute the self-weight for the structural elements. So we need to add a super dead. So you can do here SD for super dead and select super dead. The self-weight multiplier will be 0, which means that we will add it to the slab and add a new load. So we have dead load, live load, and super dead. After that, click OK. Now we want to define load combinations. Go to Define menu and select Load Combinations. Add a new combo. Name it 1.4 and click OK. Now add a copy or add a new combo and 1.6 live. Linear add for combination type, and for dead this is 1.26. Add, and this for super dead will also. To start modeling the project, we need to drawing the grids. Drawing the grids, let's go to AutoCAD. In the X direction, we have A, B, C, D, E, and F grids. So let's add them in ETABS. To add them, click here and add modify grids. Modify show grid system. In the X grid data, we need to add first one and name it A and add up to E. First coordinate, we don't need the ordinates, we need spacing. It's more simple. So we have A to C to E. The first spacing is 2.5, which is the cantilever, and you can see here the second and the last are 8 meters. The last one will be 0 because this spacing is 8 meters, so the spacing between D and E it's 8 meters. And for the Y grid data, let's see in the AutoCAD that grids that crossing the Y direction. This is Y direction, and this is the grids that crossing the Y direction. We have 1 up to 6 grids. So let's add them. Add them A1, 2, 1, 2, 3, 4, 5 up to 6. So this is 8 and 8, and all of these are 9.5. And the last one would be 0. Can change the bubble size so you can see it, and maybe the color. Okay, and then click OK. Refresh view. In this lesson, we are going to draw the first floor and modeling it. First of all, you need to make sure that the grids are, we have A to F grid, and this is the spacing, 2.5, and all of them 8 except the last one as spacing. And for the Y, we have also 1 up to 6. The last one will be 0, and these are 3, 4, 5, 9.5 meters. And the first one and 2 will be 8 meters. So here we have our grid. We need to draw the columns. Go to this tool, Quick Draw Columns, and select C50 by 70, which are the columns. Make sure it is Draw Object using grids. Click like this, and here we have the columns have been drawn. Delete unnecessary columns. For example, these we don't need it, and this we have this cantilever will be like this, and here we have here a beam, and it will be like this. So these also we don't need them. Here for the cantilever we don't need these columns, so delete them. Now we want to draw the beams, all beams in the X direction and also Y direction, in addition to this inclined beam, and we have other two inclined beams here, are 90 by 50 centimeters. Go to the first tool, which is Quick Draw Beams. Select the object or the property type to be 90 by 50, and draw object using grids. At the same way, draw the beams. Make sure to extend the beams here for the cantilever. So this will help us in the design. The same way for the Y direction. Note that this beam will be 0.4 by 0.4, so don't draw it now. Here we have also a beam. Now we want to draw the inclined beams, but before that, here we have a shear wall, so we need to delete this beams. And to draw the inclined, choose this tool, choose the property to be the beam 90 by 50 and straight line for line drawing type. Click the grid point. After that, right click, and here also again, and here we have also. Now we want to draw the 0.4 by 0.4 beam cantilever beam. To draw it, go to this tool and select 0.4 by 0.4 and draw it. Now to draw the circular beams, go to this tool and select the frame 60 by 40 and select arc center 2 points. Click the first point here, the second point here, and the third point here. After that, click right click. By the same way, we need to draw this part. So go and select the arc center 2 points, 60 by 40 beams. Select the first point, the second point, and the last one. Right click, finish. Now we want to draw the walls, shear walls. Draw the shear walls, go to quick draw wall. Select type of area beer and the property. Our wall we have defined was 350 millimeters of thickness, and draw object using grids. And select this and this line or grid, so we have draw it. If you cannot see the extrude, you can click on this extrude view toggle. So default like this, you can extrude it and see the dimensions. Now we need to draw the slab in this area. To draw the slab in this area, first of all, we need to divide these to circular beams because ETABS need a segments to do the analysis further in doing the matrices and so on. So select them and go to edit frames, divide the frames, select 10 or 8, 10 for example, or 8, apply. So you divide it. If you don't see these labels, go to the set display option and select labels and then apply labels for the joints. And also you need to do to go to draw menu, snap options, deselect them all and select only these 3 options, apply. So we can snap to the joints that we need. Now go to this tool, draw floor, and straight line for the edge drawing type. Select the waffle, slab 40 property, zone, so we need to draw it. Select the grid, and you can snap into these joints and draw them one by one. And finally click in this column, grid point, double click, and the area is created. Also you need to do this, so click in the joints, the same procedure. And here we go, the area is created. Now we need also to use quick draw floor. So click in this and use draw type object grids and choose the same property and click in these panels to create other areas. Now you can see we have this area and we don't need this part. So to delete it, we need to click in this area that we created and also this beam. So select them, go to edit shells, divide shells, and choose the first option and click on extend frames to shell edges and apply. Choose the unneeded part and delete. To draw the opening, we need to add a reference point at this corner. As you can see, the opening are 3000 by 6000 millimeters. So go to draw menu, draw reference points. For the x, I will choose this point, so the x will be 0.7/2, which is 3000. Here is the y, will be the half of 0.5, so it will be 2250 millimeters, and the X direction will be 3,350 millimeters. Click the point. Here the point is created. We need another point at distance 3,000 millimeters for the opening, and this is 0. Click at this point, so it has been created here. We need another 2 grid points, one here and one here, for y equal 6,000. So for x 3,000 and we need y 6,000 millimeter. Click at this point. As you can see, it's created here, and maybe we need to make this minus 3,000 and click this point, so it's created. To draw the opening, go to this option, this is option, which is draw floor per or wall plan view. Select straight line and opening. Choose the first point, second point, and third one. The last one, double click, and here is created. You can now uncheck the assignments for labels on joints and apply OK. And here is the first floor has been created. In this lesson, we will learn how to assign the base reactions to be bin. Go to plan view and move down so you can see these restraints. Select all of them and go to assign menu, joint, restraints, and select the bin 1. Translation X and Y and Z are not allowed and apply. Hello and welcome again. In this lesson, we will learn how to assign slab loads. To assign slab loads, first of all, we need to select the slab object. Go to select menu, select by object type, and choose floors. Select, close. Go to assign menu. But before we go to assign menu, ensure that you already defined the load patterns, dead, pipe, and super dead. The self-weight multiplier for the dead is 1. And also the load combinations. 1.4 dead and 1.2 dead plus 1.6 live. For 1.4 dead, you can see it. It is 1.4 by dead and 1.4 by super dead with a combination type linear add. The same thing for 1.2 dead plus 1.6 live. Then go to assign menu, shell loads, uniform. From super dead, 3 kN per meter square under gravity, apply. And choose live load, 5 kN per meter square under gravity also, apply. You need to select the slab, so go to this, previous selection, and apply. If you check any slab, you can see loads are 5 live and 3 kN per meter square for super dead. Now we need to assign the perimeter wall of 6 kN per meter at the perimeter of the building. So select all the perimeter beams. Make sure you selected all things, all the perimeter beams and these divided. Then go to assign menu and frame loads, assign frame loads distributed, and choose. We need first of all to, maybe we don't need to define a load pattern for the perimeter wall. We can just add it as super dead. Super dead of, here's the uniform load per meter. So it is 6 kilonewton per meter, and click apply. Close. As you can see, it's applied. So we have loads 6 kilonewton per meter of additional super dead in all the perimeter for the building. Hello. In this part, we need to assign beams for each groups. So in this beam, in the X direction, it is a B1. So we need to assign it. Go to assign window and select assign object to group, select B1. And for this also we have a B2, so select them and choose B2, apply. And repeat this process. B3, B4, B5, B6, beam 7 in the Y direction. This 3 spans, B7, and this B8, B8, apply. And this will be B9 and B10, B11, and these inclined beams are B12, apply. And this beam is B13, apply. And the cantilever, which is 0.4 by 0.4, it is B14, apply. And finally, the cantilever beam. Select it. First of all, go to set display option, and for joints, uncheck it, apply, close, select like this, and click for the slab to unselect it, and also for the beams, click on it. So we have 17 frames of the divided cantilever beam assigned to B15, apply. For the columns, we can do this. Select object by object type, select columns, and assign for now, assign all of them to C1, and maybe we need C2 later in the design step, but for now, choose C1. We have 20, so apply. And for shear walls, this will be W1, so select it and apply. And this will be W2, apply. Okay, close. And you can see we have defined the groups for all structural members. See you on the next lesson. Now we need to replicate the first floor with all assigned groups and load combinations and load assigns to the first floor, story 2, story 1, which is the ground floor, or so we have story 2 and story 3. So we need to replicate the story to the other stories. Let's see the 3D view, and also we can open a new window. And for this window, change it to plan, story 1. So we have 3D view and a plan view. So yeah, to do this, we need to select everything. So you can select this and go to edit, replicate, or you can press Ctrl R, go to story, select 2 and move up, select the second story. So story 2 and story 3, and make sure to modify show replicate options for assigns, click on it. And so we have 8 joints of 9. So we need to, this is diaphragms. You can select it, but it will not affect. And here we go. This is 29 by 29. 18 of 19, you can see it is diaphragms. So all is selected. Diaphragms is for the systemic design. So you can check it or uncheck it. It will not affect this design project. So after for links, we have 2 of 2, and so click OK. So now we have 59 of 59 to be selected. which means we selected everything correctly, and click Apply. Make sure to select Story 2 and 3, Apply, and see here in the 3D view we have replicate the stories. So you can see now this is our project. In this lesson, we need to know how to make extrude. Extrude tool helps you to understand how the orientation for the structural elements such as columns, beams, walls, and slab. So to do this, you can press here extrude view toggle, but you need to do something before we click on it to make sure that it works. Go to this tick, the display option, and go and make sure to for spatial effects, click on object fill and object edge. You can also click this for extrude frames and extrude shells. Apply. Okay. And here you can see it has been extruded. You can unextrude it by click this button. Also, you can change the extrude style from extrude view for frame objects to extruded view for shell objects. So this is the shell, and this is for the frame. You can check it. So it has been created and extrude for the frame. Also, you can for this transparency toggle, you can take it for the frame objects or for shell objects. Let's see frame objects how it looks. So you can see what is changed, and here extrude view for shell objects. Also, you can see how the slab is. In addition, you can change the colors symbology. To change it, you need to go to set display options and go to this first option, general view by colors of objects. So every object has a color. So all beams have the same color because it's the same object as beams and columns, slabs. But you may change it regarding the section properties or based on material properties like steel and FC prime, but everything is FC prime, which is concrete, or in groups. For example, B1 has a color, B2 another color, and so on. Let's see section properties and look how it's changed. Apply. Again, section properties, apply. You can see how it's changed. So every section has a unique color. In this lesson, we will talk about how to draw design strips, column strips, and bindle strips according to ACI direction method. To do this, first of all, we need to go to set display options. Make sure to make a tick for layer A and layer B. Those layers will indicate the column strips and bindle strips in the direction X for A and direction Y for B. Also, you need to show this strips, so we need to go to other assignments and make sure to select labels and show width so we can see them later. Apply. To draw them, there is an automatic way. Go to edit and click add edit design strips. Add design strips using grids. We are in the story one, and our grid system for direction we'll choose first of all X, and it will be layer A, and make sure to select auto, so software will automatically compute the width according to ACI code. Apply. And here Ctrl Z because we need also to make a middle design strips, so we need middle strips and column strips for the layer A. Apply. And you can see, for example, here there is a column strip A1 and middle strip A1. Also, we need to do this for the Y direction, so Y and layer B. Apply. So we have make these design strips that will help us to design the reps for the slab in the next lessons. For now, we need to set the meshing for the 3D or for our building, but for that we need to do replicating these A and B layers for design strips to floor 2 and 3. If we go to 3D, we have already in the floor 1 or story 1. To select them, go to select menu, select by object type, and select design strip A and B, control by B or shift to B. We have select them. So go to edit and replicate story, select 2 and floor story 2 and story 3 and click apply. To unshow them, go to set display option and turn off. So we have done this step. The second step, which is our lesson today, is to meshing this building. Mesh means to divide the floors and beams into small rectangular or pieces so that the software will make the matrices and do the analysis. Go to Analyze and make sure to set degree of freedom to be full 3D and go to Analyze. Again, automatic mesh for floors. Choose general mesh. So the software will make a general mesh because there is some circular beams will not be rectangular the meshing pieces here. So general mesh is the best solution for this case. And because our building is just 3 floors, we can make it 0.25 meter for each mesh size. But if we have 20 floors, it will be so hard for rendering and for the software to do the analysis. And maybe it will be the software may stop. So 0.25 or 25 centimeters, it's okay, and click OK. To show this mesh, go to the set display option and shell analysis mesh, general shell analysis mesh, apply, close, show undeformed shape, make sure again it's turned on, shell analysis mesh, apply. It will make a few seconds, close, and here we go. This is our project and the meshing for the floors has been done. As you can see, it's small pieces for the floors. Also, we need to do this for the shear walls. So to do this, go to Analyze and go to Automatic Rectangular Mesh for walls and choose the same size 0.25 and OK. So look at these shear walls. They will be divided. So you can see creating analysis model software doing the task for us. And we finished. To show the fixations or pins for the footing, go again to the set display option and choose joint objects, apply, and we can see they have been added. And see you in the next lesson. Hello, in this lesson we will do the step before running the analysis, which is to check this model or the structural building that it's okay and there is nothing need to be modified. To do this, go to Analyze menu and go to Check Model. We will check the joints and frames and other checks for stories and machine loading and other things. So select all, but unselect trim. So I don't need the software to trim or extend anything because I need to see whether if there is a problem, and if there is an issue, I will change it by manual. So click OK. And he is creating the analysis model elements, and this is for the assigns, loads, and he's ready. You can see this message and it says model has been checked no warning messages were generated. So our project is good. Now, after we make the check from the analysis, check model, now we want to run the analysis. To run the analysis, go to this option, run analysis, or you can press F5 or go to analyze menu and click run analysis. This will take a few seconds. Wait after he is finished. And here is the final result. Refreshing the window and to see the results, for example, displacement, deflection, we can see the deflection from here, show deflection shape. From live load, for example, apply, we can also add wire shadow. So we can see the original position for the structural elements, and to see it, you can view the 3D view. And here you can see, here is the deflection. And you can see the run has been done. Also, you can see moments, diagrams, M33. We'll talk about it later. From live load, for example. To show the moment, you can click on display frame in this tool, or F8, and select live load or the case you want, or maybe the combinations, for example 1.2 plus 1.6 live, and include the frames, file diagram. Also we can see the values, M33 for moment, and apply. If you cannot see it, click on show undeformed shape and click it again, apply. You will see these values for moment diagram. So this is for running the analysis. See you in the next lesson. Hello, in this lesson we will learn how to do the compatibility check. Compatibility check is a check used to ensure that all structural members have been defined and seated in its position, and every member is connected to other member correctly. To do this, we need first of all to make sure that you have run the analysis. If you don't see the start animation button here, you need to unlock this unlock it, so you can unlock the model and rerun again, run analysis. After that, you will see this button, start animation. Start animation, and you can see here processing animation frames, and you will hear some music. And you can see we can speed this, so we can see everything is working together, and there is no any structural member such as beam column out of its position. So everything is perfect. This is called compatibility check. In this lecture, we will do the equilibrium check, which means summation of fx equals 0, summation of fy equals 0, summation of fz equals 0. And we will do this for base reactions for the gravity, so it will be in the z direction. So we will see summation of fz, which means the structural loads of dead load, super dead, wall, and live load, equals 0, which means we will do this, and so we do click on display menu and show tables. After making the run analysis, go to structural output and check it, and check only for the base reactions. After that, select load patterns. We need all dead load, live load, super dead only. Load cases, we don't need modal. Select the dead, control, live, control, SD for super dead. Combinations, we don't need them, so clear. Okay, and okay. You can see the FZ kilonewton for dead is equal to 2000, 28,495, and so on for live load and super dead. Now going to PowerPoint, we have did this screenshot. From live load, we will do the equilibrium check. The net floor area, you can compute it using AutoCAD or by ETABS. You can click on this slab for each panel and compute them. So you can find the property area. So we found the total area of one floor is equal to 8, and I mean by net area, not including the opening. So you will subtract the opening area, which is 3 by 6 meters. This evaluates to 899.27 meters square. So the total life will be in the load base reaction, this area by 3 floors by 5, which is the load live load. This evaluates to this value, but from ETABS we have this value. We compute the error, which is the difference between this absolute difference over the ETABS value, because ETABS, it is the correct one. The error will be 0.000 something, so it is less than 10%, so it is acceptable. For super dead, the total super dead base reaction is 899.2, and this is the area from AutoCAD or ETABS by 3 floors and 3 kilonewton, which is super dead only. The super dead, I mean not the wall. The wall is 6 kilonewton, and here is the calculation for the wall. This evaluates to 800. The wall super dead, we can compute it by computing the total perimeter by your calculator or ETABS or AutoCAD. You can combine them. So the total length will be 146 meters by 6 kilonewton, which is the unit length, unit weight for the wall load, and by 3 because we have 3 floors. This evaluates this value and this value. So the total will be about 10,800.6 kilonewton. And therefore, from ETABS, it's 10,721 kilonewtons. There is an error here for this value. So this is equal to 8,172. So therefore, the error will be 0.7. Even it is more than 0.7 for this value, it is less than 10%, so it's okay. Equilibrium check for dead load. To compute the dead load, we have floors and columns, beams for each group, and also we have shear walls. We will compute for each one by one. For dead load for floors, we have total area for one floor, net area by 3 floors, and unit weight, it is 5.55. This is you can find it from the catalog. If you found the catalog for framework for the waffle slab, there is a catalog shown that the self weight of the slab will be 5.55 if you use a specific catalog for a framework. And this is evaluate this value. For columns, you can evaluate it by, we have 20 columns by 3 floors, so it is 60 columns. This is the number of columns, and this is the dimensions of columns. This is the height, and this is 0.5 by 0.7 all the columns are 0.5 by 0.7 dimensions. And 21, which is the unit weight of reinforced concrete, we have inputted, and this is evaluate this value. For beams also, you can find the total weight by the total beam length. You need to compute them. So by 3, which is 3 floor, and the cross-sectional area for the beams by 21, which is the unit weight of reinforced concrete. So you need to do this for all beams. Each group, we have 3 groups, 50 by 90 and 40 by 60, 40 by 40 centimeters. So this is evaluate these values. And the walls also, you can find it by, we have the height, and we have 2 shear walls by their cross-sectional area, which is 0.35 thickness, and 8 the length of one shear wall by 3 floors by 25, which is unit weight of reinforced concrete. And you can combine them together. You have this value, and from ETABS we have found it here to be 28,495 kilonewtons. So we can find the error. It is about 4%. So it is less than 10%. So it is accepted, which means the deflection sustained load. So delta L is unsustained load, and delta LS is sustained live load. And we can assume that sustained load or unsustained load are equal to 0.5 total live load. So also for lambda is equal to psi over 1 plus 50 rho% or rho prime. Rho prime, it is the compression steel, and assuming we also in the design we design the structural members for mainly for the tension steel. So assume there is a compression steel of a minimum, which is equal 0.0018. Therefore, the lambda will be psi is for the long-term deflection and is depending on the time. And assume the time is infinity for the structure, so it will be 2 according to ACI code over 1 plus 50 rho prime. This evaluate the factor 1.83. Some engineers take it 2 or 1.9. This depends on the rho prime, which is the compression steel. But in our case, we can assume there is minimum of compression steel. Therefore, this is the factor. So we combine them, 1.83 by dead load plus super dead plus 1.83 by 0.5 live load sustained and 0.5 load live unsustained. So they are 0.5 from total life and plus 0.5 from total life. If you combine them, 0.5 plus 0.5, and yeah, by the factor 1.83, this evaluate 1.415 live load, and this is for the dead load plus super dead, because you know the total dead is dead load plus super dead. So this is the combination that we will design or check in the deflection. So going to ETABS, going to undeformed shape, we go to define menu and load combinations, add a new combo and name it deflection long term deflection. So we need to add 1.83. Also we have the live load, which is the fact 5, and it is a linear add. So this is our combination. So linear add for combination type, and okay. Also in the design for the next chapter, we need an envelope for these first and 2 combinations. So add a new combo and select envelope for combination type and name it envelope. And here we need to add the first one, and the scale factor will be 1. And this is the second combination, so it will be the envelope 1 for these 2 combinations. So here we have defined the long-term deflection combination. Okay, and now we want to see the deflection from this combination. So go to this icon, show the form shape, or you can press F6 and choose the combo, which is long-term deflection, and ensure to check the contour options, draw contour So we can show the contour in this building, and we can see the symbology. And click, you can take this where shadow, see the original state, and apply. Waiting for reading the results. And here we go. We want to check this panel, so zoom in. To check it, first of all, our units, you can see for the length it is in millimeter. So we will read millimeter deflections. For example, it's about 32 millimeters. But this 32 millimeters, it is relative to the beams here. So we need to compute the average of the deflection in this panel for these beams, and compute the average, and then we will subtract this value from the average. So it will be the correct answer. To do this, you can see here it's about 5.7. So 5.7 plus 10.1, 5.7 plus 10.1, and here it's about 9.8 plus the value here about 17, which equal 42.6 over 4. So it's about 10.6 millimeters. So this is the value, 32.6 minus 10.6, which evaluate to 20 millimeters. So this is the value for the slab. It's about 20. And the average deflection for the beams, it's about 10 millimeters. So the maximum deflection from ETABS, it's 32.6 for this panel in the middle, and the average deflection for the surrounding beams are 10.6. So 32.6 minus 10.6 evaluate to this is 22 millimeters. And the allowable deflection for rigid partitions, we can evaluate it as L over 20, 240, which is according to ACI code for rigid partitions, unlike glass. So it is will be 42, 420. But in this case, it is rigid partitions of blocks and shear walls, so it's about 33.3 millimeters. So this means that slab is adequate for deflection. Thickness is adequate for the deflection. Also, our beams are stiff enough, so they are 50 centimeters by 90 centimeters. So the deflection will be also adequate. And this is for the serviceability check for deflection. See you on the next lesson. For now, we will talk about how to initialize the column reinforcement to ETABS. So the ETABS will design the columns based on this reinforcement. To do this, we will estimate the area of steel, which is the steel ratio. Steel ratio ranges from 1% up to 7%. To be more economic, use 1%. So it's 0.01 in decimal by the area gross. Area gross of column 500 millimeters by 700 millimeters. Evaluate 3,500 millimeters. We can use 560 millimeters, for example. So this area by the diameter gross area for 516, which is pi d square over r, where d is the part size in millimeter, and this equal 17.4. We need to approximate it to the nearest integer, 18 by 16 millimeters. For the distribution, I distributed it like this. We have 6 bars in X, and here also 6 bars. So the sum is 12. Also we have 1, 2, 3, 1, 2, 3, 6 bars in Y direction. This and this and this. Also in here, 6 plus 12 evaluate to 18 bars of by 60 millimeters. Now for the reinforcement of stirrups, we have an external stirrup of 510 millimeter, and forget the distance now. In ETABS we have 3 direction and 2 direction. 3 direction will be in the short, according to its orientation, how it's drawn. So the short dimension will be 3 direction, and the long one, which is 0.7, it's the 2 direction. Now we will use this stirrup, but we don't need to make also an internal stirrup or middle stirrup to confine this stirrups or these bars in the middle. And this is because if we evaluate the distance between, for example, this distance 500 millimeters, so distance between each two bars is center to center is equal to 500 millimeters, which is the total distance, minus we have cover here and cover here, two end cover and cover of 40 millimeters, and we have also 10 of stirrup size by 2. We have in this end and in this end, minus the bar size because we need to compute center to center. So we have a half diameter and here a half diameter of bar size. So 16 over 2 by 2 because we have two end. It's evaluated to 16 over the spaces, number of spaces, 1, 2, 3, 4 spaces, and this evaluate to 96 millimeters. And according to ACI code, it should be less than 150 millimeters. And in our case, it's okay. And you can do this for the other dimension. And also it will be adequate. It will be evaluated about 120 millimeters or something like that by the same way of this procedure. For now, in summary, we have 18, 5, 16 millimeters. And you can see in the third direction, we have 1, 2, 3, 4, 5 bars, and 1, 2, 3, 4, 5, 6 bars in the 2 direction. And we have 1, 5, 10 for stirrup. Now going to ETABS, unlock the modal so we can define and modify the frame section. Go to frame section C 50 by 70, which is our column, modify, and go to reinforcement. Ensure the longitudinal rebar grade 60, which we have defined, and our cover it's 40 millimeters. We have in 3 direction as we explained, 5 bars and 6 bars in the other axis, which is 2 direction. We will use 516, so use it. And here for the bars we have confinement bar of stirrup 10 millimeter diameter, so it's about 79 millimeters for 2 leg. Also for 1 leg, so the ETABS will use this value to design, and we can put spacing of 200 millimeters for now for you. And for the number of confinement bars in 3 direction, we need to make like a line. This is the third direction. We need to make line that perpendicular to this direction, and the number of legs that crossing of a stirrup, the number of stirrup legs that this line crossing, we will input this number. So this line crossing this external stirrup of 1 leg, and this is a 2 leg, so we have 2 legs. So in the third direction, the number of confinement will be 2. Also in the same procedure for 2 direction, this is the perpendicular line, and also it cross the 2 leg of confinement. So input 2. Okay. See you in the next lesson. Hi. In this lesson, we will talk about the design load. So make run for now. Before reading the design and design step, we need to make sure that our design code what we want. So go to concrete frame design in this icon and click view revise references. Ensure that our code is ACI 318-19, and go at the last, before this, the last one, which is 28 item, which is pattern live load factor. In our case, it would be 0. So click OK and OK. So this is for our lesson. See you in the next lesson. Hi, in this lesson, we will learn how to select the type of frame our project. So it's way ordinary. You need to select everything. So you can do that by Control A. Control A. So we have selected everything. 20, you can see in the left corner, 20, 105 joints and 5 frames. So yeah, to do that, go to this concrete design and click the second option, which is View Revise Override, and change the framing type from what is exists. In my software, it's way special. So this means the reinforcement will be large and special, but in our case, it's way ordinary. So click on it and OK. And we have changed it. See you in the next lesson. For now, we will talk about how to select the design combination, load combination, and the envelope one. To do that, go to concrete frame design and go to select design combinations. Select the 1.2 dead plus 1.6 live and the other one 1.4 dead, and click in this arrow and leave the envelope one. Also deflection, we don't need it, but in the design, the software will automatically design in the envelope, which is we have defined. As you can see, you hover about it, envelope type, envelope of combinations of these two combinations. So just add them and leave the envelope in the left list. Okay. Now we will talk about how to select the design groups. To do that, go to the concrete frame design and select design group, and choose all these groups except the C2 because we don't have a C2, as we explained. All the columns for now, at this moment, are called C1 in group C1. So add them and then click OK. Hi. What we did for now is only for the frame members for frame design, concrete frame design. But we need also to add preferences or some customizing for the slab. So to do that, go to this icon, concrete slab design, and click in the arrow and click on View Revise Preferences. Go to minimum table. As you can see, it is 15 millimeters, and we need to change it to 40 millimeters as the bottom one. And the preferred bar, usually 512 or 514, so use 514. And inner slab rebar layer, select anyone for now. And this is two-way, select two-way, and ensure the code is ACI 318-19. And OK. Click OK. And this is for this lesson. See you in the next lesson. In this lesson, we will learn how to select the design load combinations for slab and the design stories for slab. To do this, go to this tool or this icon and select first of all design combinations. At the same way as we explained for the frames, select the first two combinations, add them to design combinations, and the rest of them for envelope, it will be the design one because it will take the envelope one of these. And then click OK. To select the design group, go and select stories for design. Select all these stories. OK. Thanks for watching. After we make all the configurations for design of a frames and slab, it's time to run and design. To do this, we need to click on concrete frame design, not the arrow, but the icon itself, which is like column or a beam. So click on it, and you can see the program or software is designing now the frames, and here is the result. As you can see, for story 1, longitudinal reinforcing ACI 318-19. For the slab, by the same way, we can click on this concrete slab design and wait the software to do the process. It takes some time, and you can see slab strip design for layer A, top and bottom reinforcement, intensity, enveloping, picture, millimeter square per meter. Now, and before reading the results, and we should make some check, and this check to ensure that all the dimensions, for example, for the frame sections are adequate for the design, and they don't need any changes. So to do this, go to this, for example, concrete frame, and at the last here we have pre-analysis, verify analysis, PS design section. So we need to ensure that ETABS has created the analysis PS design section. It is the same, and there is no any iterations that need to be done, like to run the design again. So it is a final result. To verify this, click on this, and we can see this message: analysis and design sections match for all concrete frames, and this is good. Also, we need to do another check, which is verify that all member passed. This means that, for example, columns don't have an overstress and they adequate as dimensions for these loads. So click on it, and also the check is passed. As you can see, a message says all concrete frames passed the design check. In this lesson, we will learn how to read the information and display them for design. To do this, first of all, we need to reading the frame design outputs. To do this, first of all, we need to make sure that we have design. So click the design and run it. Wait for the information. So this is our information for beams. If we zoom in, and for this beam, there is a letter called I and letter called J. I for the starting and J for the ending for this beam. So these two values, 1459 and 1141, these two values are, as you can see, are the I end top and I end bottom. So I end top, which means top steel for I, for this end. For this end, there is top steel, and also a bottom steel of these steel's values. And in the middle, also we have 969 and 1593 bottom and top steel. Also for the J, which is this end, we have these two values. We can change the, for example, if you go in this, and you can shift Ctrl F6 or display design info, go to this option. This is called, this output is a total longitudinal reinforcing. You can change it to a percentage. For percentage, it's more better for the columns, because we interested in the ratio, which is 1% to 7%. We need either this column economical or not in design. You can see there is a second option, shear reinforcing. So we can choose shear reinforcing and apply. So we can see this is the shear values. In the middle here in the middle, we have 130 millimeters AV over S, and here 82.69 AV over S. S, which is spacing, and AV, which is the number of legs by the stirrup confinement diameter for area of steel. And also you can see there is a lot of options. For example, column bending moment interaction ratios, and torsion reinforcing, apply. So there is a lot of torsion, because this slab will make a torsion in this beam, and there are the AST and ASL, where AST the torsion and ASL the summation of area of steel for shear, the normal shear, and area of steel AT over S, which is from torsion. And you can see also for the end and I and J, and in the middle, these values. There is a lot of options. Torsional longitudinal reinforcing also. You can see these values, and there are here the same. This indicates that it is a minimum value. And this is for the frame. We can see the output design for the slab. We can display picture design from here. And there is two ways, strip based and finite element based. Strip based, we have A for X strips and B for Y strips. And we can set it as area per unit width. We click apply. You can see the values, but first of all, we need to go to see the result after you make apply. You need to turn on the layers. So go to set display option in this tick and turn on the layer A and layer B. For now, we are going to layer A to read the layer A. So layer A, apply, and you can see these results. You can see, for example, this beam for each middle strip and column strip. There is one. There is here tube steel, and you can see it like in millimeters, as you can see, per unit width. Also, we can change the output to be. Here is the number of sides, as you can see. We select the bar size top and bottom to be 6 millimeter. But also here there is an area of steel of 42 millimeters, so we need another 1 by 6 millimeter. We can change it to area per unit width, apply, and here's the area per unit width, millimeter per meter. So we know the width of the scoring strip and also the middle strip, so you can find the values as you can see. Also, we can see the total rebar per strip, and this is millimeter per the whole strip, 1188 millimeter, and there is here is the value, and you can read it. Also, you may need to check the slab design, and this we will discuss it later. Hi, in this lesson we will talk the another way to output the design for the slab, which is finite element method. So go to concrete slab design at the right arrow, click on it, and go to display picture design. But for now, select the finite element based. And for now, uncheck the imposed minimum reinforcing. And you can see here there is a lot of options. There is for direction 1 a top rebar, so we can show a top rebar needed and make a contour. Click apply, and you can see there is here a contour. Here is the coloring. So here this color is for 700 millimeters needed, and you can see it. You can hover and focus. Here the values are in yellow, about 500 millimeters or 460, 470, and you can check the area of steel that needed for this slab in the direction 1. And you can see in direction 1, which means the reps in this direction, in X direction. So for top, it will be in the support, and here the values are 0, as you can see. So the top mainly is the top rebar or top reinforcement is mainly on the supports, rather than the bottom rebar in the same direction. So the coloring will be this contour like this. You can see in the middle there is about 300 millimeters needed, and you can see in the middle for this panel, if you go above, so the values would be smaller. And also you can do this for the other directions, for top rebar in the Y direction, and also the bottom rebar in Y direction. Also you can make a contour range. For example, I need the minimum, let's say 200 millimeters per meter, apply, and I can do this imposed, and also for the maximum we can say minimize it to be, for example, 150, and you can see all the spans are 0, which means you can do this quite 12 each 15 centimeters or 150 millimeters. This will be good for top rebars in the direction too, for these strips in this direction. In this lesson, we will talk about the design of beam, and we will design the beam manually, and then we will compare the result with ETABS. First of all, we need to select the beam. So our beam that we will check is in the 3rd floor, and this is our beam. You need to show the moment 3-3. So go to member force diagram, or here display frame forces. Select M33, and you can select show values and fill diagram for frames. Apply. Right click for our beam, which is, you can also go to elevation. So it is in 1, grid 1, apply, close. And here is our beam. Right click. And here is the maximum tube steel for a moment 285. So this is our moment, and we will see the design. So click the design and go to this arrow, display design information, and ensure to select flexural reinforcing. Apply. Now the values changes. Right click at this beam at this end and click details, zoom in, and here we can see the moment, which we have C 285.2, and this needs 916 millimeters, but the minimum that ETABS calculated according to ACI code 1221 millimeters. So we need to do the calculation manually and compare with these results. If C prime, it is 28 megapascal. If yielding for steel 420 megapascal, and B for the beam, it is 500 millimeters, and D it is the depth, the total depth, which is 900 millimeters minus the cover, which is 60 millimeters minus the stirrup size diameter, and minus assuming the bar reinforcement is 16 millimeters, so the half will be 8, and this evaluate to 822. Area of steel will be the 0.003, which is 1.4 or 1.4 over Fy, according to ACI code for beams. This is the rho by the B by D. This is B and this is D. We calculate here. This is evaluate to 1294 millimeters. In the next slide, this is the equation or formula to compute rho 0.85 Fc prime over Fy by 1 minus square root of 1 minus 2.61 M ultimate, where M ultimate in Newton millimeters. So we need to calculate the moment in Newton millimeter by multiply by 10 over 6 over BD square, and those in millimeter, Fc prime in megapascal, which is 28. And also you need to compute this. It will be 0.00227. If you multiply it by B by D, it will evaluate the area of steel that needed. And this is the moment. And remember, this is area of steel we computed. But you can see 935 millimeters is less than the minimum steel we calculated. Therefore, we will use the minimum steel as ETABS calculated minimum steel. But there is a difference. If you calculate the error, it is 1294 minus the ETABS value 1221 over the ETABS value, and this error will be 6%, and it's accepted. We will talk in this lesson about the torsion reinforcement of beams. First of all, we need to start design. And after that, go to display design info. You can see there is a lot of options. We have, first of all, for torsion reinforcing, apply. Select this beam, details, zoom in, and here is the details. So we have a moment rebar, and this is for the moment. For reflector, this is for the torsion. And there is a T threshold, which is the limit according to ACI. So if T ultimate, which is the torsion, less than 5 T threshold, then the beam will not be designed for torsion. So here 5T critical, which is the 5T threshold, and the limitation according to ACI code, and A naught in centimeter square, which is 0.85 from AOH, and PH, the parameter of effective torsion. Also, we have 80 over S millimeter square per meter. So per millimeter, it will be 0.38. And there is a minimum value. And here is the AL. AL, which is 80 over S plus AV over S. The total torsion, the total reinforcement, longitudinal reinforcement for torsion and for deflector, according to the ACI formulas. Also, we can display shear plus torsion reinforcing, apply for the same beam. And here is the details, 80 over S, AL, and PH, AO. And this is the torsion. And here, this is a shear reinforcement. The ultimate 2 is 0. And design moment, this is the moment. This is T ultimate, as you can see. Also can display the pictorial, the torsional longitudinal reinforcing only. So this is the total, 80 over S. Will be the same results. But if you do this, for example, go to elevation for grid 1, apply. You can see 940, which is the torsional longitudinal reinforcing. And you can change it to shear. And this value will be 80 over S. AL over S, which is 80 over S plus AV over S. To show the shear reinforcement, go to display information, design info, and here we have shear reinforcing. Apply. We can see for this beam and also for the column, AV minimum and AV major, and AV minimum. AV major 0 because the shear in column 0. So the AV minimum will be 583 millimeters. And if you know S, assume spacing S, so AV over S, you can distribute the straps over the length of this column. Here we have 0 for the I, and for the J we have 128 for this beam. In the middle also 128, which means if the number is uniform or the same, this means maybe it is the minimum. So if you click on it, you can see for shear reinforcement. This is for the shear. So we have shear force, 0 shear force. But we have 5 VC. This is 5 VC. So it will be the minimum. And also you can set the other options for shear. If you want to display the shear plus torsion. You can set it, apply, and you can see the values here. As you can see, AB over S plus 280 over S, according to ACI code. So this is the AL. This is evaluate to AL. Now we will talk about design of columns. To see the design of columns, first of all, go to 3D so we can see the whole building. Go to this option and display design information. But now we need to total rebar percentage. Total rebar percentage. Apply. And also we can make something from the Modal Explorer. We can go to structural objects. For example, story 1 and columns. Right click, select, and here right click, show selected objects only. So now we are seeing, also we can do this. Select story, go to story 2 and columns, select. Also for story 3, columns, select. Or we can do this, select by object type, columns, select them, have 16 columns, 20 in each floor, and show selected objects only. So here is the percentage of columns. As you can see, most of them are 1%. Most of them are 1%. Let's see if there is something above the 1%, which is recommended. You can see this column. It's 1.41%. This is because it is in the cantilever and maybe it has a moment, large moment. So all of them are 1% except this one. So this one will have a unique reinforcement. But we can do this. Verify all member passed. So it is passed, but it has more steel ratio, and this is because again it is in the cantilever and maybe it has some moments that make the software to use this value. Now we will talk about interaction diagrams for columns. To see the interaction diagram for columns, rather than finding in the internet the interaction diagrams and or draw it by using Excel, by hand calculations and then using Excel, this will be so hard because the ETABS allow us to use interaction diagrams, and these interaction diagrams are drawn by ETABS automatically. So to see these interaction diagrams, go to Define, Section Properties, Frames, and select the C5070, which is the column. You can click Convert to ST section or copy to ST section. Click on it, and you can name it what you want. But for now, click Section Designer. And this pop-up you will see, this is our reinforcement, and this is the reinforcement. Go to this interaction diagram surface, and you can see here the 3D interaction surface and the plan one. So there is 3 options. You can include phi or exclude phi, or exclude phi and decrease Fy. We need to include phi. And here at 0 degrees, you can find these data, P ultimate and M3 in kilonewton meter. And also, if you set the angle to be 90 degrees, you will see M3 will be 0 and M2 will be evaluated. So you can copy these values and draw it using Excel, and then find, for example, whatever the column you need to check for a moment. You can find the P ultimate or axial load from ETABS, and then you can plot this point in this curve, and if it is under the curve, this means that this section is adequate to carry the moment and axial load together. And if it is not, or it is so near to the curve, if this point is here near to the curve, or it's touching the curve, this means the section you need to increase the steel ratio, or may you need to rechange the dimension of this column. So they are so helpful, these interaction diagrams, and ETABS offer these interaction diagrams for free for you. The design of columns. Again, you can go here and display design information, total required percentage. So we have the percentage for each column, and therefore, again, supply. Okay, we will go here and select object type, columns, select rows, and click show selected on. So here is the percentage. I will unshow the horizon, apply, close, and also I will turn off the grid. So here we have these columns. All of them are 1% except this. So 1% means that the section we defined, which is here, define this section. We have 5 bars in the third direction, 5 bars and 6 bars in two direction of 16 millimeters, and 5 10 millimeters of stirrup confinement, each 25 centimeters. So this is our design, and you can see it by convert or copy to SD section designer, and here you can draw the bars and distribute them from this section designer. There's a lot of tools, so you can draw like this, draw bars and lines, and there is a lot of options. You can do this and try it, but this is for the 1% area of steel, and for the other one 1.41. So if you calculate it, 0.014 by the area gross, which is 500 millimeters by 700 millimeters, this evaluates to 4,900 millimeters. So divide it by 16 square by 3.14 over 4. So this evaluates to 24.3 of 16 millimeters. So you may round it to 25, or the best solution is to increase the size bar. So assume it is 25 or 20 millimeters of bars, and compute the area of steel, and you can distribute them such that the distances between bars not larger than 150 millimeters, and if so, you need to add the middle stirrups according to ACI code, and you make a unique detail for this column from the ground floor to the top floor, and other columns will have the same detail except this one. We will talk about the slab design, exactly the design for ribs in the slab. So go to this slab design and click on it. And you can see here for default slab strip design layer A, which is in the X direction, top and bottom in millimeter square for flexural, and we need additional at some points. So go to this and click display flexural design. Here we have make it none if we apply, and to see the reinforcement we must go to this and show A and B, close, going to plan for story 1. So here, as you can see, the intensity in millimeter square per meter. So this is this distance is 8, and 8 over 4 evaluate to 4 meter. So this column strip is 4 meter width. So this value 245 millimeters. It's envelope flexural design for the ribs here in this 2 meter, because the column strip it's 4 meters, so 2 meter outside and 2 meter inside. So the first 2 meter of this panel, the ribs in this area will have in meter 245 millimeters per meter. So our ribs are 0.8 meter. Distance between rib and rib, it's 0.8 meter. So you should divide this area by the width of column strip first of all. Then you need to multiply by 0.8 to find the area of steel that needed for the one rib. And this is for the column strip. Also, there is another way, like you can show total rebar area for strip, apply, and this is, we have 491, 491. And also we can specify the number of reinforcing, for example, in layer A, top rebar of 12 millimeters and distance 150. And you can apply. So 0 means it's satisfied. If you make in this area 12 millimeter, a distance equal 15 centimeters, this don't need any additional reinforcement, and this is will be good. This is for the strip based, and there is another display type which is finite element based. To display the shear reinforcement for the ribs in the slab, go to display pictorial design and select strip based, and display type, choose shear reinforcement and choose apply, and here is the reinforcement for the ribs. Here for the middle strip, column strip, column strip. So you need here about 400 millimeters. This is exactly 395 millimeters 0.8. So this is, if you click on it, you can see these diagrams. So here is the moment, and you can see all the details. This is the length, and this is the distance to rebar center, and here is the other factors. And you can see down the longitudinal reinforcement in addition to shear diagram. So our shear maximum X is 67 kilonewton, and here is the transverse millimeter per meter, millimeter square per meter, which is AB over S. So it is 395, which is 0.39 millimeter square per millimeter. This is in meter, so you need to divide by 1000. So you have AB over S, and you can compute S or assume S. So you have the bar size, or you can assume the bar size and compute the spacing between these stirrups. And here is also for the shear diagram, and here is the moment, and you can see the shear is maybe it will be less than the minimum. So here is the shear, and AB over S required will be 0 in some cases. So you will need to use the minimum area of steel in the ribs for shear reinforcement. And this is also for the middle strip, and you can see also for the layer B, which is in the Y direction. Also we have a column strip, middle strip, and column strip, and so forth. You can also this is for the shear reinforcement, and you can see it's millimeter square per meter, so it's not in millimeter. If you would like to change it to millimeter, you can change the units, consistent units, show units form, and change this from millimeter square to meter, millimeter square, or choose millimeter, will be millimeter square per millimeter. Okay, and here is changed. So this allows you to read it quickly. Now we will talk about how to use the another method, which is finite element based, to show the output design for rips in this slab. So go here, slab section, slab design section, and display flexural design. And for now, design basis will be finite element based, not strip based. And here we have only flexural reinforcement for this case. So apply, and you can see here for bottom bar direction 1, we zoom out, zoom in, we have value 0.29 millimeter square per millimeter. So this is the area of steel needed for the reps in this direction, in X direction or direction 1, in bottom steel. For top steel in the same direction, also we need 0.2, 0.3, 0.3 millimeter square per millimeter. Also, we can specify a number. For example, I am showing top bar, so use 12, for example, at distance 250 millimeters. And you can see where the color here indicate that the value 0.13 or 0.14 is an additional. So you need to add an additional reinforcement to 12, 5, 2, 5, 12, each 25 centimeters. Additional to this reinforcement, you need 0.14 millimeters per millimeter. So convert it to a number of bars and add additional reinforcement here. Also, sometimes in the opening, you may need, we change a bottom, apply, and choose 12, for example, 200 millimeters. So it's okay, but if you make it 250, see what happens, and you can zoom in. So here in the opening, you need also 0.02 millimeters square per millimeter. So this is additional reinforcement you should add here in the opening, and this helps you to reinforce each area. And know that the reps will be continuous. So if they are needed here to 514 millimeters for these reps in the X direction to prepare, so they will be continuous from this starting point to this end point at the cantilever circular beam. And this is also for the Y direction, for top steel and bottom steel. Now we will talk about shrinkage reinforcement for the slab. We can use or make a strip of 1 meter or 1000 millimeter, and this is the rho or the formula to assign the shrinkage steel to the slab. A as minimum equal 0.0018 ph, where B is the strip width, which is 1000 millimeter, and H is the thickness of the slab, which is 40 centimeters. So this evaluates to 720 millimeters square. So I suggested to use a top steel of 1 phi 10 each 10 centimeter and 1 phi 10 each 10 centimeters for both top and bottom directions, as you can see illustrated in this image. Now we will talk about how to create user report from ETABS. To do that, go to File menu and create report. Choose this one, add a new user report to make the customization. From general, I need this list of tables, figures, and cover page, contents, and so on. Multi-step outputs for the envelopes. Round combinations, I can choose the envelope 1 and long-term deflection. Groups, I can check all of them. C2, I don't need it. And here, I need this from dead load and live load, modal, and super dead. Also for the load patterns. For definitions, we can output the story data, grid systems, point coordinates if you don't need it. You can check, uncheck. For the assignments, we need the summary for frames and joints, and for shells also, distributed loads. The outputs, we need the base reactions and displacements. Okay, for the design, we need the concrete frame, overrides and preferences, in addition to envelope results, and also for the concrete slab. After you make all of these changes, click Create and wait until the program make the summary report. Waiting, so it's writing a table, strip versus summary. And now the program finished the report. You can see we can zoom in, and this is the 3D view, and here is the table of contents for loads, for example, and we need the design tables. Here is for the story, grid definitions, and everything. Here is the groups that we have for beams and floors and walls. These data are strip object conductivity related to design strips, and here are the assignments for groups. We need for now frame sections. These are the frame sections and the materials. We can move down so we can find such these data. The B, absolute maximum strip forces in story 3 location and in this span from the model, and this is the force. And this is the overrides for the columns. It's way ordinary for our frame system. And this is the PMM envelope for the columns. You can see the steer ratios for all columns are 1%, except this 1.4, which is C31, has a unique name 6, unique name of number 6, and this is the locations. This is the location, and this is the TP ultimate on it, and the combination it's 1.2 plus 1.6 live, which control this design. And this is also for other columns are 1.1 and 1.2. So you can discover every design, all the design data, for example, area of steel bottom for concrete frame, for a flexural envelope, and also for the torsion. You'll see it in another table. So this is how to create a report, a user report from ETABS. To export the design data, go to tables. First of all, show the Modal Explorer by going to View or Options, show Modal Explorer. Once it's shown, go to Tables, Design Data, Concrete Frame, and there is a summary for beams, columns, and join design. We need the beams, so right-click and export to Excel. So here the software is initializing the data, and we can see the Excel has been shown here, and all the data has been exported to Excel. For example, there is here area of steel top and area of steel bottom combination, minimum top for the beams, and maybe we can do this, Control A, and go to page layout, right to left. So here for the story, and here is the label. This is for story 3, beam 1. Here is the station, at station 250. So all of this is beam 1. And these are the stations. And here there is a status, no message, means no message error. Area of steel top combination, that control, and area of steel computed. Here is the area of steel top, and minimum in bottom, area of steel bottom, and the combination for shear, combination for shear, and the rebar in AVO as AVO for us, in millimeter square per meter. So all the information about beam and the design of beams has been exported to Excel. So you can combine them and make the job drawing you need in AutoCAD and summarize what you want. Hello, this is the last lesson of our course, and it's about the job drawing of this project in AutoCAD. So here are building layout, list of drawing, and general notes, column layouts, beam layout, slab layout, and the reinforcement in direction 1 and direction 2 for the ribs, and beams reinforcement in addition to the last one, which is columns details. So here is our plan, and this is the grid, and we have all the necessary layers have been added. Here are the general notes, and also here is the column layouts. So this is C1, C2, C1, 1, C1, 2, C1, 3, and this because the percent it's 1.4, so it's C2, 1, C2, 1, and you know this C1, 19, and this is another one. So in the one floor we have 20 columns, and this is the layout of beams, our beams, and this beam will be a circular beam, and here is the section in the slab, which is section AA, and this is the section AA, which have 1, 2, 3, 4, 4 ribs, and half of 2 framework of office slab. So here we have 1, 2, 3, 4, 4 ribs, and there is 2 half of framework at the ends. And here is the reinforcement, 2, 5, 2, 5, 10 millimeters each, 10 centimeter, and 1 by 10 millimeter each, 15 centimeters. And this is also another section in the slab, which is typical section in column C1, 17, showing the overlapping. It's about 1 meter and between the floors. In addition to the reinforcement for stirrup, you can make it maximum, and dense. You can minimize the distances between stirrups at the first quarter of span, and in the middle you can make it just a minimum, so you can increase the spacing in the middle, but at the ends you need to make them dense. And here is the waffle slab. You can see from the plan or top view an opening. So this is slab layout, and this is the reinforcement for ribs, top reinforcement and bottom reinforcement, in addition to writing for each reinforcement the length for these bars. And there is also an overlapping, which is LTD according to development length according to ACI. And this is for the another direction, and here also for beam 1, 50.90 centimeters, and this is the scale. So we have torsion reinforcement in the middle, and top reinforcement and bottom reinforcement, and you can see the overlapping LTD and the hook LDH according to ACI code. And here the extent, it's about a quarter meter centimeter or 15 centimeter. And these are the dimensions for the top and middle and bottom bars accordingly. And also this is for beam 2, and for other details there is a table showing each beam and the top, bottom, middle, and stirrup reinforcement, and also the middle layers for torsion. As you can see, for the beam 1 we have stations, so station 1, station 2, station 3, station 4 or section 4 up to section 9, showing the reinforcement at each station. And also we have a standard hook in addition to middle stirrups where it is should be added. And this is for our columns. We have 2 groups of column, section C21 and C1, 1 up to C1, 19. So 19 plus 1 to evaluate to 20 for each floor. And this is the details in addition to table we have here. As we explained, it is about 18 by 16 millimeters, except this one, it's about 10 by 25 millimeters. And this is for the chop drawing. Also, this is a table that we exported from the user ETABS report, and we make groups using Excel. So we have for each beam the design for shear and design for bottom and top steel for reflectoral, in addition to torsion. After that, we do these tables by combining them and take the maximum one, or you may need to plot and draw for each beam a detail like this, a profile that's showing each details for top steel, bottom steel, and middle steel. And this should be taken according to development length, LTD, and the LDH, according to the ACI code. And thanks for watching.